Hi guys, welcome to the Advanced Manufacturing Summit, and this is my session on Fusion FFF and hybrid manufacturing. So join the session to hear about Autodesk and Renishaw's journey in utilising Fusion 360 to create an advanced end-to-end workflow. This journey will move from initial generatively designed part design, process simulation, additive manufacture, and a unique post-processing solution using Fusion FFF. For those who don't know, FFF stands for Fused Filament Fabrication, and it's also known as FDM, which is Fused Deposition Modelling, which is a name trademarked by Stratasys. We'll also touch on another customer story with ALM, discussing the benefits and combining multiple tools with new materials to additively manufacture a high-performance part. My name's Tom Stock. I'm a research engineer and I work for the additive product team at Autodesk. I work in the Birmingham facility, and you can see that's me on the right. And this is me in my first year, just fitting an extraction system to our KUKA robot cell. And this is kind of my first project involving additive, and this is what piqued my interest and led me to where I am today. And I don't know if there's anyone else here but I was also graduate of University of Warwick, and that's where I got my undergrad and my master's in mechanical engineering. Before we continue, just a bit of disclaimer. So we may make statements regarding planned or future development efforts for our existing or new products and services. These statements are not intended to be a promise or guarantee of future availability of products, services or features, but merely reflect our current plans and based on factors currently known to us. These planned and future development efforts may change without notice. Purchasing decisions should not be made based upon reliance of these statements. These statements are being made as of August 2020, and we assume no obligation to update these forward-looking statements to reflect events that occur or circumstances that exist or changed after the date on which they were made. If this presentation is reviewed after August 2020, these statements may no longer contain current or accurate information. So this is the part that we want to tell the Renishaw Autodesk story with. This is the NOV Keminer impeller. NOV are the customer, and they produce various machinery and equipment, but their expertise lies in supporting the oil and gas industry. The part itself, it's a gas dispersion impeller, and effectively what it does is it mixes fluid very efficiently. These are usually measured in terms of feet, so they're quite large, and to manufacture them they use large-scale manufacturing operations such as brake press, plate bending and welding. But the ones we want to look at, these are quite small and they're measured in terms of inches in diameter, and these are used in pilot and research plants to kind of focus on the next generation of reaction and fermentation technology. And by focusing on these small ones, these small parts first, companies can get the edge before moving to large scale. Now, of course, small scale parts provide very different challenges to large scale, especially manufacture. So this was the opportunity for NOV and Autodesk and Renishaw to work together to develop this part. So we began looking at the original CFD to see how the part performs. So we were looking at this and thinking, okay, how can we improve the part? The blades, of course, these work already, they're proven, so we've not got much design freedom. Looking at the hub and shaft, again, we've got very little design freedom here, and this is difficult to make the difference. But we started looking at the disc, the central disc that held the blades to the hub. And we started asking questions like, is there a need for it to be this way? Is it important? Is it critical? Or can it be changed? So what we did is we removed it and we just kind of isolated it or simplified the design down to the blades and the hub. And this is where Autodesk felt they can make the difference. This is where we felt we could increase the manufacturability of these small scale impellers to minimize costs. So we thought this was a case that maybe generative design would work well for. So generative design is an iterative design process that gives you kind of numerous outputs for a given set number of constraints. The great thing about it gives you, hundreds of solutions that maybe a team of people could not have conceived. And this is all within Fusion. So we created a setup, we ran studies, and what we did was we decided to look at 1/6 and focus on the connection of an individual blade to the hub. We created preserve and obstacle geometry, and we set up load cases. And of course, we looked at different materials that we could use. So with regards to the manufacture of this part, this is where we started considering additive. Additive, of course, is great for low volume and outside the normal kind of operations of manufacture. And this part fell into that category. And with the objectives, we really focus on minimizing mass and therefore cost, as well as increasing manufacturability, because this is what NAV wanted. And of course, this would mean if we were to do this, then we'd be successful in what we wanted. And so here we go, we ran some generative studies, and you can see from the studies there was quite a few outcomes, and this is just kind of video showing you some of the ones that we look at. Obviously we wanted to find ones that lowered the mass, but of course we wanted to find ones that were still manufacturable, and this is where we went to Renishaw for their expertise. So this is the first kind of design that we gravitated towards. We were looking at this and thinking, okay, manufacturability. How manufacturable is this for an additive process? And this is where we went to Renishaw. And then we started asking the bigger questions like, well, how would we orient it? How would we support it? What is non-negotiable? What happens after the build? So it's interesting, if you look at the bottom picture on the right, you could see that maybe this is not a suitable orientation. This is not a suitable part, So we need to find an optimal orientation, and so we'd have confidence in the support structures. And because overall we wanted a successful build. And I mean successful in terms of getting a part at the end that has the desired quality that we'd want. So we went back to Renishaw and tried to draw on their vast experience with builds, orientations and support. And this part here, this is a bracket and some small discs. These are some issues that they faced in the past with builds like this. You can see that actually during the build the discs become loose and get pushed around by the ricotta. Of course these ended up failing, and not only would it lead to a failed build but also possible damage to the ricotta. And with the bracket itself, well, it actually didn't turn out much better. It failed as well. And if you actually look at it, you think, oh, maybe why did it fail? We had supports, we designed it for additive manufacture, but of course then maybe you look at the process simulation and you actually see these areas of support was always going to fail. You can actually see a picture of the disc at the end of the print. It's just a glob of material. So this leads us to then ask very important questions about our own part, about our own NOV impeller. So jumping back to our part, the main restrictions we were finding for additive are function and material. And the three problems we were facing with the design of this impeller. The first one was performance. The part had to, of course, meet or surpass the performance requirement dictated by the simulation and the previous design, and meet the requirements placed by NOV. 2, the availability of materials for additive, especially SLM, is quite limited and it's growing. So we need to find, a material that's suitable for this part using this new additive manufacture process. This part, it didn't want to be too heavy. It's going to be spinning at a high RPM. And also, of course, it's got to be particularly corrosion resistant. It's going to be mixing with oils and various other fluids and be under constant use. So one of the materials that we started to look at was titanium alloy, Ti6Al4V. So of course this is an expensive alloy, so it really leads us on to think about reducing the overall material usage. And this would lead us on to our third problem and consideration, so printability and support. So we want a successful build. Kind of the less support and the better orientation means less titanium used, and it's a faster build and it saves cost. Now with the current design, as we had at the top right, you can see the arms kind of joining the blades to the central hub or shaft are not an effective solution going forward because of the manufacturability issues. So the arms that we would have to design would serve two functions, kind of this hub blade connection and also self-supporting, so they do not need support structures underneath them. And so we could reduce material usage and go back to what NAV wanted, which is improve the manufacturability, reduce costs. And I could talk how we went about this on the next few slides. So again, going back to the design, you can see in the top left, that was the first design. We kind of thought about the bottom left. This was some ideas that were getting thrown around about creating this arm that could somehow be at 45 degrees and not need support. And so we went back to generative design, ran more studies while working with Renishaw. And the top right is this new hub blade connection that we came up with. And you can see a representation of the part with those new arm structures in the bottom right. And we can see the benefit regarding support usage on the next slide. Now, this is all well and good, but as mentioned previously, with respect to Renishaw's past experience, process simulation is important because you can design a part well, but you don't know necessarily how it's going to build. So we've got our new design in the top left with kind of the orientation chosen and fully supported. And we generated our mesh, as you can see at the bottom left, for the simulation, the SLM simulation. And you can see just in that kind of middle central picture, we've got our simulation settings. And so on the right, if I play the video, you can see we've got our simulation for SLM manufacture. And as we move through the part, you can see the areas of max displacement / distortion, where they're going to be in the build. So, having looked at the simulation and knowing the build would be okay moving forward, we then create the setup for the build. So we actually wanted to print 4 of these impellers, and we wanted to print it with Renishaw on their Ren 500Q machine. This is a quad laser machine, and as you can see, this is in Fusion creating the setup, and got this kind of simulation of the tool path, and we're looking at it as a per layer basis. And you kind of zoom in and you can see the hatches and the borders. And we've got our build strategy / build style selected, and now kind of having set it all up, we're ready to start building. And this is a great simulation from Renishaw's Quant AM software of the build, just moving up through the layers, showing you how the part's going to be built. Fantastic. So we generated the MTT file, loaded it onto the machine, and this is a video of the build. See, there we go, the Ricota's just laid the powder. And we've got the lasers, as I said, it's quad laser, so we've got 4 lasers. At the moment it's just creating the support structures. And then once it's done with the supports, it'll move on to the central hub, as you'll see. This is the first few layers that's been printing. And of course, if you watch carefully, see it's building the central hub profile. So you can see actually that there is a loss of efficiency here. You can see the kind of where there's 2 lasers printing, and while the other 2 have stopped. So if we look at the 7 wastes, we've got the weighting waste here. So we've got a bit of loss of efficiency. And of course, you could also say we've got the loss of efficiency of the powder spread, where actually the build is kind of a pause in the actual build process itself while the Ricota has to lay the powder. Cool. So this is the parts having come out of the build. They've built really nicely, and I think this is probably one of the best pre-post processing builds I've been involved with. They printed really well on the machine, and actually now that you can see they're on the build plate on the right with the powder cleared, we now have to get them off. As many people might know, having dealt with stuff like this is where it starts to get messy. And this is where you kind of go to the archaic process of support removal. There are machines now that automate this process, and it's good to see because it's catching up with the kind of technology itself. But often they have to be, people have ripping them off or they get machined off. So this was our kind of next step. Having removed most of the support, we also wanted to machine some of it away. So this is now our post-processing stage. And how we went about holding the impeller was using this machine block that we put in the jaws, and then we bolted the part through the top, as you can see in the left picture, and bolt it through the central hub. Now, if you watch the video, you can actually see a relatively large deflection under low load of the blade, So you can see just how the dial moves. So this is obviously quite worrying, and if you watch the video and listen to the sounds, you can just see the tool comes in contact with the blade, listen to the sound, it doesn't sound good, and then right at the end, you might hear me swearing, so apologies for that, right at the end the tool broke. So we can actually see with a zoomed in picture of the tool's chipped, it's broken, and there's an awful chatter finish on the surface of the critical surface of the blades. So looking at this is not going to work, and we're running out of time. I was at Renishaw's Additive Solution Centre in Kitchener. I was only there for a week, and we were trying to go through this whole process in the few days I was there. And we realised quickly that the current idea that we'd done, the setup, was not going to work for this machining of this part. So we had to kind of go back to the drawing board. So we had to get creative as well. So going back to what Renishaw have done in the past with these kind of formal jaws, we thought maybe that's an option. But Renishaw had problems with these jaws. So the issue that they found, and you've even got this bottom left picture, you can see it's quite inventive rubber band solution here. But if you look at some of these conformal jaws, what Renishaw have been finding, these difficult parts, you could put them in the jaws in your machine and it all seems to work fine. And then when they were taken off and inspecting the part at the end, this is where they've seen that they were so far off. And what's actually happening is that they're so far out of tolerance because the part was actually being bent by the jaws. So it's been held in a position in the conformal jaws. And as soon as it was taken out to be inspected, it actually kind of deformed. It went back to its normal deformed rested position. And so it's actually everything was out. And so we knew this wasn't a solution for us going forward. Again, drawing on Renishaw's past experience with this kind of thing, they brought up this kind of new innovative solution to holding difficult parts. So this is this UV activated glue fixture, also known as like the blue photon fixture. So it's very interesting how it works. It uses this UV curable glue on these kind of inserts, and actually you just literally glue the part down. Awesome. So incorporating this blue photon glue fixture, this was the solution that we came up with. You can see each one of these blades are being held. So this is a 3D printed fixture. So obviously we'd had issues with machining. We needed a fixture to hold the blades properly for machining, and we needed something quick. And so this is something that we came up with. It was printed overnight out of carbon fibre. And it holds, this is a fixture, and it holds these inserts with the glue on that holds the individual blades. And this is great because it printed overnight and printed it quickly. So we had something in the morning to hold our part for machining. And I'll give you a breakdown of how it works on the next few slides. So you can see we've got our impeller and we've got our gripper. And that's offsetted from our blades by about 1 millimeter. So the blades being the critical surface for machining. So this is what we need to hold. Because these surfaces are important because they're the ones driving the mixing of the fluid. So we had our fixture, we offset it by 1 millimeter. We've then got our insert, and it holds the gripper in place and makes sure everything's aligned. But now we need a fixture to hold these in place to the blades. And this is where, of course, our 3D printed fixture came in. And this is how it held them. So you can see a sectional analysis all within Fusion. You can see how the gripper's offsetted by 1 mil, as I said, and you've got this kind of very slight flanges either side of the insert, and it's not a large contact surface to play with, but it was enough to hold the part really securely. And here we go. So this was the part actually having been designed, and this is how we set it up for manufacture within Fusion. So obviously, as I said, we'd had an issue with the original fixture, so we went back into Fusion to create this new part to hold these blue photon UV curing inserts to hold our blades for machining. And I can play the video, and this is us having designed the part, creating the setup, and printing it directly from Fusion to a printer. The printer that we used was actually the Ultimaker S5, but I'll show you that in the next slide or so. And what was great about this is we could just stay under the one Fusion roof. You know, there's no back and forth, no data exchange. We stay within Fusion. We had the impeller already there. We just loaded in the CAD data of the inserts, designed around them, designed around the impeller, and then we could just simply click print and generate this part and sent to the printer, and then we had a fixture to use overnight. You can see it just post-processing, very quick. So here we go. This is the fixture having been sent to the FFF printer. This is the Ultimaker S5 that we used, and actually the filament that we used, the material that we used to print with, is this Colorfab Carbon Fiber XT filament. It's quite different to normal 3D printing filament in the terms that it's 20% carbon fiber, so it's a lot stronger and stiffer, and this is of course key for machining. Is it as high performance as maybe a metal fixture? No, but it meets the requirements for our low machining forces. See, it's just the print head doing the infill now, building up in layers. And hopefully all it needs to do is just hold the blades firmly and stiffly so there's no chatter. And of course a better hold would lead for a better surface finish and a better overall quality. And actually interestingly, this material had an 84% tensile strength of aluminium, so it's very stiff. Fantastic. So for those who are interested, this is the printed fixture, and you can see me just fitting in the inserts, and they fit really, really well. And then we've got the central pillar as well, so that's just to kind of place the central hub of the impeller on and gives us a reference for aligning the part with the grippers. And on the right, that's Carl from Renishaw just applying the glue, the photosensitive glue, ready for curing. You can see this is the glue applied, and we've got our UV light source, and all it needs is 90 seconds of curing to get a full set, and we do 3 at a time. Perfect, and there we go. That's the impeller fully held by our fixture and the blue photon inserts. And now once the glue's set, the light sources were removed, and now we can just put in a chuck and we're ready for probing and machining. So we jump back into Fusion and we create our probing setup. We set up our points, and we've got, you can see a nice simulation of the probing path within Fusion. So this is the 3-2-1, and of course this is also known as plane line point alignment. And you can see how it's been set up here. So this is what we use to do the initial alignment of the part. This is it in action, and it does the plane line point. So it's just the plane, and now it's going to do the line, and then that final point. And of course, this is where kind of a bit of the magic happens. So we've got this product called MSP NC Perfect Part, and this is a post-processor that we use within Fusion that basically does the kind of magic of aligning the part. NC Perfect Part wasn't available commercially at the time, but it's just used by us for this project. And you can see it doing the 3-2-1, the plane line point alignment, and you can see the points being plotted on the part on the right. And if you go into MSP, you can see the full report with the deviation of the points, and you can see how it needs to do the alignment to fit the part. You can just see that again, that unalign and alignment. Fantastic, and then we can proceed when we're happy. Now of course we can align anything with a 3-2-1, so further alignment is needed. So that's where we go into the final alignment with the blade. So again you can see it running through the probing, the simulation of the blade. You can see on the left then the real life probing of the blade. Points being recognised in MSP NC Perfect Part. So we can see our alignment results. Again, we've got this full report. We can see kind of the deviation per each point. And clicking proceed does the final full alignment of the part. And then you can see the results. And again, one final report just showing you with the new alignment, with the new coordinate values. Fantastic. Now we're ready to proceed with the machining. So this is where we cross our fingers a little bit and hope it goes better than the last time. Yeah, this is where we did have confidence in our work in the fixture. Go spindle and the coolant. And now hopefully we get a much better machining sound. Yeah, sounds much healthier. Fantastic, and of course the programming of the toolpaths was all done within Fusion. Great, and we can see that much better surface finish that the tool has given to our surface of our blades, and there's a happy customer at the end as well. So to summarise our journey. So the original model, we remodeled it in Autodesk's generative design. We did the SLM process simulation. We did the build preparation as well. We also went back and had to do the fixture design and then printed it on an FFF machine. And then there's the part alignment with NC Perfect Part that I've just talked about. And then of course the final post-processing stage via subtractive manufacture. So apart from the remodeling with Autodesk Generative Design, the rest was actually done in 3 days. So I flew out on the Monday and was with Mark Kirby from Renishaw on the Tuesday, and then flew out on the Friday, so just 3 days. So we could operate within this time frame because we could stay within Fusion 360, stay within the software for the whole workflow from end to end. And this was helped by the use of workspaces within Fusion. So you can see on the bottom right, we've got a list of some of them there, and then some screenshots on the far right of some of those individual workspaces that were used, like design, manufacture, and simulation. And so therefore, you don't have this constant data exchange in between different software with potential loss of information. And the great thing is you've got this one continuous digital path. So if you wanted to say, come back in 6 years again, all you have to do is just regenerate everything that's here and everything will update. And same again, if you want to go back and change something at the very beginning, again, everything would update. And that's just the great thing, that's the power of Fusion. So that summarises the Renishaw and NAV project. Now I want to talk briefly about the ALM partnership. ALM stands for Advanced Laser Materials, and it's a company that operates within the EOS group. So the project that we collaborated with them on was a project to redesign a high-performance mountain bike pedal using various tools, including Autodesk Generative Design. And we did this redesigning with the focus being on the material, using ALM materials. And of course, a lot depends on the material in terms of the design and manufacture, so this is something that we really focused in on. And the real focus of this project, therefore, was about bringing and testing these new materials into Fusion. During the course of this project, 4 new ALM composite materials are being brought into Fusion. So doing this and working with companies and creating partnerships like the ones we have with the ALM allows us to bring in new materials so that these kind of companies can then use our software and use their own materials. And it's kind of this bringing of all this like know-how and knowledge together that create something quite special. And this is an ongoing project, so keep your eyes open on this. You can see we've got a couple of designs on the left and top here, and then the ones that have been printed at the moment. So we used a variety of tools for these, mostly all done in Fusion. So there's more to come on this, so please keep your eyes open. Thank you, fantastic. So that's everything I have to present on. I hope you guys really enjoyed the session, and I hope you guys really enjoy the rest of the summit. Thank you.